Hi. Here we get started. I'm Renu Raman here, Vice President in SAP. We'll talk a little bit about what we're doing in our cloud infrastructure. And I use the word SAP data because there's a storage view of the world and there's a memory view of the world, and a little bit of both is what we'll touch upon. This is not necessarily at a very low level in terms of how we architect from the media layer up kind of talk. It's more a little bit of tops down, high level view down, and touch upon a few key things on resiliency, availability, as well as get into some of the new usages with something like 3D XPOINT and storage class memories, and how do we end up using it, at least for the short term. And long term is going to be somewhat different. I have to give the boilerplate disclosure on there's nothing that I'm saying here is going to be can be used in your stock trading, or nothing representing about future implications of what products and other things we do. And anything and everything I say here is subject to change and etc. So can read the fine print. There's quite a bit of area I cover. There's a list of people that involved. It's not, I'm just representing quite a number of people involved in this area in storage and NVRAM and other things. So with that, there are 4 or 5 areas of I'll cover. The data strategy that we have, the current status of what we use in storage, which is historical and traditional, which is file, block, and emerging object in terms of what we have today and where we go forward with it, and some of the key things we consider in the design point especially as we move forward on the design point. And increasingly, the storage problem is becoming a networking problem, and I'll touch upon that a little bit. Then a little bit looking into the future, it's coming probably the next year or two, is how do we deal with NVRAM, 3D XPOINT in particular, but NVRAM in general, and some key considerations as we go forward downstream. With that, let's see, at the highest level, what is SAP is all about? If you look at the Gartner definition of applications, there's mode 1 and mode 2. If you know, mode 1 means legacy applications, and mode 2 is all the future-looking. One called as microservices, componentized, refactored, and cloud-enabled is mode 2. Mode 1 is traditional ERP, CRM, and those kinds of monolithic applications. And obviously, all of this is based on a foundation of data, and we run analytics and other applications riding on top of the data that we have. So it's abstracted in a very simple at a high level. And if you open that up a little bit, this is the way it looks in how SAP views the world today. Oops, sorry. Let me go back. Is the SAP Cloud Platform. So on the left is mode 1, mode 2, that's the past and looking into the future. And going from the bottom, we rely on multiple infrastructure, including SAP's own infrastructure as a service, as well as we made enough announcements about leveraging GCP, Azure, and AWS, where our applications are running in these cloud properties. Laid on top of the IaaS is the SAP's in-memory database HANA, and increasingly Vora, which is a distributed analytical database, much along the lines of Hadoop and Spark, but enhanced with SQL and all the enterprise use cases. And of course, there's going to be a plethora of different databases used by the developers, whether it's MongoDB, Postgres, and others for many of the applications. These are all open source databases and open source storage. Laid on top of that is a variety of APIs and functions, which is embedded in the PaaS layer, which is SAP Cloud Platform. And there's an API hub, and SAP applications will be. This is the high-level software architecture, as well as the business architecture, if you will. So simplifying that is, if you look at where we want to be, where we are today and where we want to go, is at the lowest level we have, as you know, hard disk, flash, and DRAM/NVRAM. And we have databases like HANA and Vora, and others emerging along with it. As we go from left to right, as you can see, we have had historically block, file, and object, and obviously with new applications emerging, we have tables, queues, streams, and KV stores that are emerging. This kind of overlays and maps with the mode 1 and mode 2. It also maps to the notion of traditional view of the storage and forward-looking view of semiconductor memories and how we leverage those semiconductor memories. With that context, where are we today? The different storage types, data types that we have in the classical sense of definition or the industry sense of definition is volume, variety, and value. The system of record is HANA, and IQ is another columnar disk-based database. HANA is a columnar in-memory database. AAC was part of Sybase. IQ and AAC were part of Sybase, which SAP acquired 4 or 5 years back. So it's a row store, classical disk-based row store database, AAC, and IQ is a columnar store. And Postgres is, as you all know, is an open source database. And then Hadoop and Vora, which gives a much higher capacity and volume and velocity in terms of use cases. We don't have much Hadoop in today except for the recent acquisition about a year back of Altiscale, which is Hadoop as a service. So I'll touch a little bit upon that. And then the general usage of storage for VMs and generalized applications and application stores. So these are the 3 different types. The historical view of what our infrastructure looks like. Today we are about 150 petabytes. So the growth over time, I've got a 6-7 year history. It obviously goes longer than that. Has been the biggest growth is in the NAS and the file. The blue line on top shows the growth in the capacity, about 7x in about 7 years' time. And the number of devices, which means the number of individual instances of boxes, traditional deployment models like an appliance, a NetApp, or an EMC gear, if you will. That's about 3x. So roughly you get 2x the growth of capacity related to the number of devices. That probably follows the density of the technology, if you will. On the right side is a graph is about the price curves. Again, this is what is the actual sourcing cost for us, the price, and then what is the effective capacity. As you can see, over a 10-year period when dedupe and compression was not mature, not available, back probably 10, 15 years back to now, obviously we see the benefits of that as we go forward. The bottom chart gives a flavor for the different types of traditional storage, file, block, primarily. There's a little bit of backup, largely in data domain. It's about 150 petabytes of total capacity, maybe 100 petabytes in NAS and various files for primary storage, for applications, and even for HANA. And then the rest of it is a little bit of SAN. So breaking down what the historical view of it, we got 150 petabytes, as I said. The growth is significant on the NAS side than the block side, which is not like traditional cloud. Most of the cloud properties use block because they serve many different applications. We know what applications that we use is all SAP applications inherently assumed a filer, or in some cases VMs. VMs also use the NetApp filers, but expose VMDK to VMware, if you will, or they have a Cinder driver for Zen and others. The other things to point out here are there are about 90,000 drives, about 10. Increasingly, there are more flash going on. It's growing at a significant rate. The failure rate that is important to consider is 1.6% historical failure, at least the last 12 months, not historical. Failure rate. Maybe it's more than 12 months. I don't know the exact, I don't recall, for hard disk versus SSD. And that's within the error bar. I mean, I've seen industry data of about 0.4% failure rate, whether it's hard disk or flash. So this translates into the resiliency and availability design point because there's a huge multiplier effect based on that error rate. So where you're focused on is improve the resiliency from where we are, because today the deployment model is like an appliance. There is a box attached to a particular compute cluster, if you will, and for a particular line of business, which is a traditional model, to a more storage as service, but also which means we have to have a higher degree of availability than we have today. So architecturally, how does it look at the highest level? As I said, there are three main type of use cases. There's HANA, the databases, a primary one, then the VM payloads, and then there's a backup tier. The backup tier, today's data domain increasingly will be an object store, both on-prem in our SAP cloud as well as the public cloud infrastructure. We try to align with industry standards. Files will follow NFS, or OpenStack is an emerging internal orchestration layer, the control plane. So Manila APIs, and then for VMs, it's Cinder. And then if you use VMware, it's vVol, and then Swift and S3 being the dominant one. The storage is operated into three tiers. There's a performance tier, which is marked in red, which is primarily driven by the database use cases in memory, and increasingly it's flash, and then going to the new memory technologies. The capacity tier is all disks, and then the backup tier is, as I said, data domain will be a combination of some combination of data domain and other snapshot-based backup mechanism with existing filers, as well as leverage the cloud properties, as well as internal S3 kind of systems. We have moved to 100 gig Ethernet, as you can see, starting this year. Sometime this year, it's already happened. All our compute clusters will have 100 gigabit Ethernet per node, which is 425 gigs. And there are reasons why we went that way. I'll touch upon that. So we moved away, or moving away slowly and steadily, from a traditional appliance model to a very simplified system architecture where the hardware is commoditized, which is basically a server with disks. The primary storage ends up being a 2U or a 1U box with NVMe drives. And the back end of it is a bunch of either dual 50 gig or 425 gig Ethernet. And it could be a rack of boxes with lots of drives. So this is nothing new and different, but than what some of the other cloud properties are doing. Layered on top is going to be emerging new distributed data stores, which is an important part. We're not developing it in-house, mostly partnered with third-party companies to find the right distributed data store, whether it's for the file or the block. That's the high-level strategy in terms of systems. So let's touch upon the resiliency design, availability, and performance aspect of what we are doing here. We have about 54 data center locations, about 13 primary, 4 that we own, and 13 are primary, big ones, where we have either significant amount of assets in terms of capital, in terms of compute infrastructure and storage infrastructure, as well as they have close to it data DR locations. And then there are other ones either co-located or through acquisitions. There are about 54 of them, and that'll shrink over time. So this gives you a map. But the key point is, as we acquire companies, the data, particularly the SaaS properties like SuccessFactors, which is HCM applications, and Ariba and Concur, you follow the sun. Customers are everywhere, so the data needs to be available across all geographic zones, and sometimes not just for DR purposes. So, as I showed earlier, what is the unit of deployment? Is a single rack with a bunch of compute, either 2-socket, 4-socket nodes. But the important thing is we are inserting. We started with thinking about a 2U form factor with NVMe, and we're just gravitating towards a 1U with NVMe drives. I'll touch upon the reasons for that. And 100 gigabit backplanes, leaf spine architecture, class network, if you will. And that's nothing, again, it's very traditional or conventional network design. So what are the key considerations in terms of resiliency? If you look at the MTDL calculations, as I told you, we have about about a little more than 10 petabytes in flash and 100 petabytes in hard disk, and increasingly more flash. So the numbers would change a little bit between 10 petabytes and 50 petabytes and others. So assuming a 4 terabyte drive, which is it's becoming commonplace with flash, used to be for hard disk, and a failure rate with an MTBF of about 100K hours for a server, and the SSD MTDF is about 1 million hours. We looked at different RAID as well as replication mechanisms to reach a certain durability, as well as we have to rely on rack level resiliency, we've had situations with this failure rate unrelated to media, unrelated to the network. A rack has burnt and gone off, particularly on a Black Friday event. So you had to protect at a minimum at a rack level, obviously, and sometimes even data center level. So that fundamentally leads us to a replication strategy. And the real question is, what is the cost of replication versus RAID? And these are simple mathematics that gets you 2 versus 3 versus 2.5, if you will, with RAID. We started with 2 and go to 3 as the cost of these flash bits come down. Expect that today, if I expect today 20 cents a gigabyte to 30 cents a gigabyte for flash drives and maybe less for the media. So it forces us to look for cheaper and cheaper flash bits to have higher order of resiliency, more so than for capacity reasons. So we'll start with two-way replication. We looked at RAID 5 and RAID 6 as augmentation to get the MTDL up to, we want to get to 1,000 years. But instead we'll make a trade-off for initially with 10 petabyte capacity, we'll start with two-way, and as our capacity grows, we'll go up to a three-way, and expecting the price of these flash devices to come down. With that, the next thing to address in resiliency is also the recovery time. So both, it's not just the cost and having enough bits, is to be able to recover fast when you have a failure. So there are two things that we end up doing. One was, as I said, we went to 100 gigabit Ethernet with NVMe and 100 gigabit Ethernet. I don't have the numbers here top of my head. You can easily achieve 2 to 3 gigabytes a second per drive, and easily get to 4 or 5 gigabytes a second per box, if you will. So any drive failures, you can do the math at 4 terabyte. We can get to sub 1 hour to rebuild. There is no data loss. Nothing goes offline because of replication. We just want to have the rebuild time to be fast. The other part to address is latency. Let me step back a little bit on the use cases for HANA, where throughput is the dominant and determining factor than latency, because HANA is an in-memory database. Most of the persistence layer to date, until we get to the new memory technologies, is on disk. But all the performance critical operations are in DRAM, so the latency is not the dominant factor for many of the operations with database like HANA. It's mostly throughput dominated. So a combination of NVMe drives and higher speed Ethernet addresses the throughput issue. Now, is latency a matter today? Not so, but as we go look forward, latency becomes an issue, especially with the memory stack that comes up. So one of the areas we've been looking at is what is the sweet spot and operating point, and what is the minimum latency we can get to. Today, if you look at all the work done in latency optimization, you have a TCP/IP stack about 30 microsecond round trip off the Linux kernel. There's a lot of work has been done with RDMA and getting the few tens of microsecond. I think the push internally, we think, is to move the part of the TCP/IP stack and many of the packet buffers and all the other handling in user space to avoid all the context switches, to avoid the NUMA effects, to avoid all the per buffer connection issues. Today we have a limitation of about 20K TCP/IP per thread, if you will, and we can push it much higher as we change it to a user space I/O, and that's the direction we want to go. Some early numbers with that is, if you take a stock Linux kernel, we can get about 500,000 IOPS and 4K with the NVMe driver, which is, I don't know which version of the OS. With the changes that are shown in the previous slide with the SPDK, we can easily drive up to 3.5. So on a per thread with the multi-queues, you can see a significant boost, especially with the number of drives attached. These are all local disks. This is not showing the network I/O yet, but we can improve dramatically the total number of IOPS. You can add to this. There's another round of optimizations coming on the network side. So that's the direction we are headed with respect to looking at the network design. The first simple the heavy hammer approach was to go to faster Ethernet and NVMe to get to improve recovery times and drive the cost down to improve the availability times as well as the recovery times. The next step is to improve the latency and what is the right protocol, what is the physical layer, what is the layer 2, layer 3, layer 4 of that is the work that's ongoing. Now, I bring up the CAP theorem that everybody is familiar with. Is only to highlight the fact that today you cannot obviously achieve all three, consistency, availability, and partition. You get 2 out of 3 that well defined. And where our optimization point as we go to the new memory stack is look at a CP system where we have either consistency over availability for certain partitions or availability and partition where we trade off consistency, which is some of the NoSQL databases have traded off that. We don't see much internally, many of the AP use cases, but I do see that coming. Many of the other, whether it's MongoDB or Cassandra and others, have gone to the AP side, and we will end up seeing more use cases internally as well. So what have we done in terms of having a rack tolerance and distributing the data with 2 or 3 way replication is just a simple animation of adding, deleting nodes and failure points. We want to have elastic scalability. We don't want to lose performance. We want to have higher availability as the scale of the infrastructure grows bigger while improving resiliency. This is a simple animation to show what happens with, in this case, I think it's 3 way replication. So if you have a node failure, there's no loss with the 3 way replication that's ongoing. We can lose even a second node, and this is a 6-node cluster, if you will. Then if a network partition failure, you do lose, in this case, when I say ACID and DLog is, what I use is a distributed log for the persistence and to manage the consistency. So you can tolerate a single node, a dual node, but when you lose a network partition, we do lose that. So that's the resiliency point we want to operate on. We can lose a 4th node or some 3rd node and a partition, and you at that point you do, in this case with a strong consistency database, you have read-write loss for certain partitions, and then you can lose HA for certain other partitions. And this is the design point we are going after from the primary storage standpoint. That used to be traditionally disk, but necessarily here we're also looking at the flash and the new media. So in summary, where are we headed? I mean, 3-4 years back, we started with looking at this problem and thought we needed to have something like high-performance PCIe SSD boxes with DSSD. We bought that. We put one of that and put it in a rack and designed around it. Technology moves fast. NVMe came in the middle. Ethernet moved up the food chain from 10 gig to 40 gig, 50 gig, and now to 100 gig in the last 2 to 3 years. So you can see the dramatic evolution of the boxes in the last 2 years, going from a 5U, 144 terabyte, custom design, custom modules, to down the bottom, just a 1U box with 8 to 10 NVMe drives is good enough. I can put a 100 gig NIC. I don't need anything more than that. We just need NVMe drives. And to going one step further, the box on the right shows even better, where you have 1 controller and 4 drives or 6 drives, because with NVMe we can saturate easily. You can do the math, multiple 10 gig interfaces. So having 1 controller and 4 drives, it becomes a failure domain. It just becomes a throwaway device. If any one of those blades die, it doesn't matter. We just with the replication strategy, we can continue to operate, and then a few days later somebody can come and replace the blade, and that gives us back to a full availability domain. Now that's just a stage about where we want to go. If this is the primary storage design point, now in parallel with Intel and others working on 3D XPOINT and storage class memory, let's touch upon the right side where we go on that topic. This is a simple-minded view of computer architecture 101, a processor and DRAM and 3D XPOINT, and then you also have 3D XPOINT on the I/O side as well as the flash. gives you a sense of latencies, going from L1 cache to a round-trip delay from a disk across the globe. So a 1 second relevant reference point ends up being 9.6 years for a round trip. So obviously that gives you a sense of the latencies. Just for fun, I just showed two planets in the middle. One was Mercury, I think, for main memory is about, if you think of Sun as the center of the ALU or the primary cache, Mercury is where the main memory is, and I think Pluto is where the 10 microsecond NVRAM is. But we look at the world as we want to look at a faster storage or slower memory. I don't want to take sides. I think the answer may be both, but that's where we are. So what are the challenges with persistent memory and HANA? We obviously want to have larger memory. The bigger the memory, it's better. We're going to be limited by the cost of DRAM as well as scalability of that. So to some extent, persistent memory addresses that capacity issue and the cost issue. The other aspect it does improve is recovery time. The bigger the in-memory state that you have, the recovery time, both the load time and rebuild time of the data structures takes longer. To some extent, we can alleviate that with the non-volatile memory. Challenges obviously is you have different latencies, so you have different NUMA problems, and other programs and programmers are used to certain latency assumptions, and they have to rethink or redo some of those assumptions. And these standards, there's no standards. Obviously, one company has one way of doing it. Who knows what will happen in the coming years, but we'll see. These things are going to be evolving, and we have to keep up with the changes. In very simple terms, how is HANA? I mean, you see the axis, you look at the variety of workloads, particularly looking at SAP's customer base on transactional workloads and OLAP workloads. Roughly 80% of it is OLTP, transactional workload, and 95% is reads. 80+% are reads, 20% writes, and then 90+% are reads, and 5% are writes for analytical or OLAP workloads. If you look at TPCC, which is an industry benchmark, that's roughly has 55% or so. So that's a little bit of an extreme. The data on the left is actual data based on SAP customer workloads. That's more than 10 petabytes of different databases lying around the planet. In very simple terms, the way HANA lays out their table in memory is what's called as delta and main. All the main database tables is kept in main, which is in persistence layer, which is in disk, as well as there's a compressed dictionary compressed format kept in memory as you load it in memory, as well as a delta, which is an in-memory, again, an in-memory copy where any changes are updated to the delta. I'll touch upon why it's kept that way. So when you looked at the optimization of how to, the design point of how to use non-volatile memory, the main was an obvious place to retarget the main and the tables and the data structures for the non-volatile memory. The delta being a smaller portion, but is really buffering or handling the writes, is best kept in DRAM as well as the temp. So what does 3D XPOINT gives us? Obviously larger capacity. Gives us the attribute of persistence, which we normally have to go to write to a disk I/O storage system. The negative is obviously higher latencies. So the intuitive way to think about why we took a very simple approach in the first version of it, and there'll be more things coming downstream, but think of that data column that I mentioned here, a column table with main and delta is decomposed into these data structures, a data table fragment and a main table fragment. And both of them have multi-version consistency because you want to keep the life history of any updates, of any changes in either of these fragments. And the delta column fragment, and both the delta column and the main column fragment is broken into three main data structures, which is the dictionary, for the dictionary compression, the main data for the column is in a column vector, and an inverted index where you want to use, say, if you want to find which rows or which columns have this particular data, you have an inverted index to look up that. So what we did initially was to map what's in red is keep it in DRAM, and before NVRAM, everything was in DRAM. And now with the NVRAM, we just allocated the main portion of the data set, which is the dictionary and the column vector, the inverted index in NVRAM. There are a couple of issues to take care of when you do that. Touch upon that. The main thing is you can't keep the pointers in NVRAM because obviously when you shut down and restart, you don't have the same pointers. That's one. And the serialization and deserialization effect, because traditionally the data layout for persistence is assumed to file in disk, and that's the other consideration. There are many more considerations, but I touched upon those two. So how does it map into the NVRAM? And this comes into what are the main APIs or mechanisms we use to map into the NVRAM. So the main column fragment with the main attribute where the DRAM look up as the anchor point to the three key data structures, which is the index vector of the dictionary and the inverted index. So that's fairly obvious from a conceptual standpoint. There's no deserialization of the large data structures for this, which means the other aspect is when we have a power failure and recovers back, you have the entire main available in NVRAM. We don't have to rebuild it. You can restart it in minutes or seconds. Then we used to take hours to rebuild that. How does it map into, did we go build our own interfaces or map into an existing, we just used the SNIA memory like the PM file abstraction. So what are the pros and cons? I mean, I can touch upon that maybe in Q&A. So what are the pros and cons of doing that? We have significant improvement in the initial phase on the restart times, more than 5x. We also have significant improvement in the memory capacity at a much lower cost, hopefully. We don't have the final cost numbers yet, but that's expectation. The new approach is we still have to have two copies. We not only have to have the NVRAM, as you know, in database, you need to have a second copy to have any node failures, to protect against node failures. And we got to also, going forward, we look at what to do with delta, which part of it could be in the NVRAM or not. Some simulation numbers that were generated as an eye chart. You cannot see it. There are 4 different charts based on this. The left one shows on the OLAP memory bandwidth using pure DRAM and then with persistent memory. The actual memory bandwidth utilized is lower because the latency is also a little higher. But there is a performance implication. The performance implication is not so much for the inserts, which is the third one in the third graph, if you will. And the fourth graph shows there is a linear performance degradation. The lower the number, the better it is. The value, all the x-axis is showing different latencies for the last 3 charts, simulated with 100 nanosecond memory to about 800 nanoseconds of memory. So there's a linear performance degradation on the right for those were selects, database selects. And the chart in the middle shows the recovery time improvement with the DRAM case versus the NVRAM case. The blue one shows the NVRAM recovery time. You may not be able to see it on the y-axis. I myself cannot read it. So let me try to finish it. What are the future considerations? I went through a lot of material fast at a very high level. Where does the platform roadmap would look like? As I showed you today, we have a 2U or 1U box which holds the secondary storage or primary storage in a secondary tier, if you will, in the rack. That's all flash today. If you look at the numbers, you have 4-socket machine, which is a basic compute block we build out. And if you map it out, you get 1 of X number, of course. But what's more relevant is we get to look at memory, both in the processor node, as in the compute node, as well as in the shared one, to have potentially look at both 3D cross-point-like structures as well as flash. But the storage obviously is going up in dramatic capacity in the same time frame. So this is the background of what it looked like in 2020, maybe a little bit different. The one thing to highlight and point out is today we have NUMA problems. You have local access of 67 nanoseconds, and then next socket access maybe is 120 nanoseconds, and if you go beyond a socket, we build a 8-way box is 200 nanoseconds, 250 nanoseconds. All that will change with increased memory capacity. Obviously, there's a core to memory ratio that's different, but we get to larger capacity, come to 2 or fewer sockets. But the NUMA is different, where we have what I call as vertical NUMA. On the same node, you have both DRAM and the secondary memory tier. You'll still have the SEM in the I/O space as well as flash. The other considerations I've not touched is data protection. There are regional, regulatory, and other considerations in terms of dealing with data protection issues. It's not just an encryption issue. All that will come into play, and how we leverage public cloud storage. So in summary, the world is still changing fast with although Moore's law is slowing down. It's all core-dominated designs, no longer clock rate for the last 10 to 15 years. And with the emergence of TPUs and others, there's other processing types coming in. So that drives Moore's law, that keeps up to Moore's law or effective Moore's law or not the Moore's law. Flash is starting to creep up, not immediately over the next 5 years, is expectation to reach HDD cost as we introduce the NVRAM tier. So we get a 2-tier memory, partly for persistence as well as memory. And then the other relevant interesting point is the network, both throughput. Throughput is just sheer economics is driving it. We're going to 10 gig to 100 gig to 400 gig. Latency is what we all have to work hard, and it's all the ideas about redoing and rethinking the kernel stack is the main area of focus. So in summary, you put all of them together, you get a dramatic increase in a single rack capacity. That's the point here is, and we have to constantly rethink the balance between price performance. More important is resiliency design point in the rack. That's the summary. I think I did. Went through fast at a high level. So, any questions? Yes.
Could you explain more about the workload?
Pardon?
Could you explain more detail about the workload?
Which one? Any particular slide? Here or so the main workload, at least for if it's related to the 3D XPOINT, we use HANA. It's the in-memory database. Is that the question? Pardon? Yes. So this particular part that I touched upon is about HANA. HANA being an in-memory database. In some part, it looks like a classical database, and in terms of access patterns from the query input side. But as I showed earlier, a traditional disk-based database. Let me go show. So there are two considerations comparing HANA versus a disk-based database. This chart shows a little bit of the read-write characteristics. The left chart, this is actually based on SAP workloads, SAP applications accessing a database, whether it's an Oracle or Sybase or HANA, doesn't matter, it gives you a read-write ratio. That chart shows industry benchmark TPCC, which shows a much higher read-write ratio than what we see today. So that's one difference. But the other higher order difference, which is not shown here, is being an in-memory database as opposed to a disk-based database, many of the latency-sensitive operations, because we write into the main memory, which is the delta, so the latency-sensitive operations are captured, and we'd have a log and a redo log structure, log structured writes, is captured in and we don't have much like a disk-based database, latency sensitivity, much more for the throughput cases where we're loading from a recovery or a failure point is important. So throughput is the dominant factor when you consider HANA as opposed to a disk-based database. So, I mean, there are a variety of other workloads that we run, but this particular one I've just shown you with HANA. The current state.
As the PMEM is getting deployed, there is a lot of traffic happening on the channel itself when the data is moving between the persistent media and the non-persistent media, right? So what is the impact of that on the latency versus regular DRAM, which is less capacity surely, but it's straight predictable latency.
So if I understand your question right, is what is the impact? Maybe the first part of your question I didn't get it right.
So the DIMMs, the persistent DIMMs, there is some DRAM and there is some non-volatile memory.
Right.
And as data is getting moved between them, let's say between the cache and the media, etc., what is the impact of that on the data?
So we don't move the main data into the DRAM. Only the delta, I think I showed you there, right, is the writes. There's a cache for the writes effectively, if you will. Reads, most of the reads typically ends up being scans. I think if you look at the prior chart, there were a lot more scans going on. So those sequential reads going on, table fragments. You can directly go to the main, to the NVRAM and read it. There is an impact for, as I said, this chart shows, right, when you do inserts, it's not much of a difference because you're writing to the DRAM, the third chart. The fourth chart shows there is a linear impact on selects. I have not shown the scans here, and you won't see much on the scans, subject to the memory the bandwidth of the PMM structure. Right. Now, having said that, there will be certain use cases, certain query types, where the caching behavior in the DRAM would help based on the access patterns. This is assumed not as much random reads that's ongoing. Right. If there are lots of random reads that's ongoing, obviously there's a benefit in bringing it in and caching it, which is not shown here. I mean, I guess we are not seeing that much in the database case. Yeah.
So more of a follow-up here. Trying to understand if you had, let's say, a 10 terabyte database, and let's say you have 1 terabyte of data. How much of the performance is limited by, let's say, the 10 terabytes in SSD, then you're moving data into the DRAM, right, for the in-memory operation? Trying to understand, like, what percentage of your performance is limited by, like, what amount of time is spent on the SSD moves itself versus, like, what is the opportunity if you had, like, a persistent memory that's faster than the SSD? How much of acceleration can you achieve just by that move, not by other
So in this particular work analysis, we're not trying to, as I said, we're not trying to cache. Again, it goes down to sequential access versus random access. If it's a lot of random access, you want to do the caching. So I don't have a good feel for which workload in random access and what is the inflection point of the latency versus that ratio to give you an answer today. I don't have. I guess in very gross terms, this is following classical caching behavior. I mean, you can just put 5 to 8%. We lose about 8% in performance for keeping 95% of the data in the secondary tier, roughly across. Now, of course, there are going to be outliers. There are going to be some queries and some benchmarks which will be 20-30% or higher. But I'm overgeneralizing it here. Yeah.
Thanks.
So other than data placements between DRAM and persistent memory, does SAP anything else to be aware of the latencies or the different latencies between DRAM and persistent memory? Other than data placement,
There's certainly many more opportunities. I think the first step here, we took a low-hanging fruit, is the way HANA main and delta is designed to do that. I think the earlier comment was, what is the other workloads which has got random access patterns to go do that. The other point is also today we only keep the persistent main piece in NVRAM. There are in-memory data structures which also contribute to the recovery time. So some of it comes into the save points. So can we do better at keeping some of that, especially from a recovery standpoint? Which the asymptote of that, if you look at it, is we'll get into the checkpoint argument and cases. From a database standpoint, there are a whole bunch of other things that I cannot talk about yet. It will come in HANA features as deal with other blobs of data and streams and other things, and especially when you get to some of the KV stores.
And do you anytime move the data from persistent memory to DRAM, or it's always getting access from persistent memory?
So the writes, all the writes will be reflected in the DRAM, in this case, in the current design point, right? Reads, if there is, from the delta you could read, obviously like a read cache, if you will, if it is the last update that was there. If it's not there, we don't try to move it from the main to the DRAM cache today. That could be an optimization that could be done, because that's not the way it was designed. It was a pure, simple DRAM design at that point. That could be you can think of that could be a natural thing based on the workload to do that next time. Okay? Anything else?
Given that the persistent memory has longer latency compared to DRAM, as we go forward, do you need any changes in the CPU architecture itself? Do you see any, like, is there more parallelism in your workloads, or like, trying to understand if there is any other change that will impact the CPU, not the memory itself?
For my memory system handling? Well, you can think of speculative reads and writes and dealing with the latency issues. People have tried to use the transactional memory semantics to deal with some of that, and there are other ideas in that.
No big dealers, it's okay.
Yeah, I mean, as the latency chart shows, the things that go farther away, I think that the point is that's an inflection point that's going to occur. There's a holy grail people have talked and did for a long time. Is I mean, there are companies like ScaleMP and others doing some kind of disaggregated memory and then dealing with that, right? There is a crossover point, I think Tom here can comment more so than I can, is when does the hardware-based caching stop, or the software-based mechanisms can take over, right? There is an inflection point somewhere between, I'm guessing somewhere between 1 microsecond and 30 microsecond, where if you have the right close small loops, you can have software to manage the other tiers. I don't know the magic number, maybe, but that's where. So I don't know if it's special instructions, but definitely there's a software mechanism to handle it. In that, when it's sub-microsecond, it's extremely hard to deal with a software-based mechanism to handle, to manage that latency. Okay? I think next is your beer or wine or whatever it is, so I'll let you go. Thank you.